This video covers section 7.7, complex numbers, for Math 95. Our goals in this section are to write the square roots of negative numbers in the form b times I, to add and subtract complex numbers, and to multiply complex numbers. You've probably heard someone refer to something as being not a real number, and you've probably even written that down as an answer to a problem yourself. In this section, we're going to deal with these non-real numbers. These are imaginary numbers that don't exist on a real number line, but it turns out that they do actually have some very important real-world applications. Unfortunately, those real-world applications don't really come up until quite a bit later in a math or an engineering program. So the goal of this section is just to get you acquainted with these non-real numbers, these complex numbers. So we're just going to cover the basics of working with these complex numbers, and that way, when you see them again, you won't be surprised. The whole idea of complex numbers comes from trying to answer the question, what is the square root of negative 1? Now, up to this point, you've probably just written not a real number and moved on with your life. Today, we're going to use a trick that mathematicians have been using for a long time. We're going to take this thing, this square root of negative 1 that is not a real number, and we're going to give it a name. The name that we're going to give it is I, little lowercase I. Now we'll do a little bit of exploration and see if we can learn anything about this new symbol that we've just invented. We know that the square root of negative 1 equals I. So what would happen if I squared my I? Take my I and square it. I'll do the same thing to the other side of this little equation, since I is really the square root of negative 1. Now, the square root of negative 1 squared undoes itself and gives us negative 1 equaling I squared. This little trick is just about all there is to complex numbers. The first thing is that we started by inventing a new symbol to represent the square root of negative 1. Then we took that symbol and messed around with it a little bit to see if anything good would happen, and we found out that I squared has to be negative 1. We can use that definition of I to write any other non-real number as a multiple of I. For example, here I have the square root of negative 4. Remember that the square root of negative 4 could be the same as the square root of negative 1 times 4, and then there was that product property that allowed us to split the square root up, making this the square root of negative 1 times the square root of 4. Now, the square root of negative 1, we just gave a special name. We're calling that I now, and the square root of 4 is also actually a nice number. That's 2. Usually we rewrite this as 2 times I rather than I times 2, but it really doesn't matter which way you go. I can do something really similar with the square root of negative 3. The square root of negative 3 is the same as the square root of negative 1 multiplied by the square root of 3. But that square root of negative 1 has a special name. It's I. And the square root of 3 isn't a nice number, so we'll just leave it in its exact form as the square root of 3. If you think that you've noticed a shortcut, you're probably right. Whenever you have a negative under the square root, you can drop the negative and rewrite it with an I on the outside. Then, if the square root happens to simplify, you can simplify that square root as well. Why don't you go ahead and take a moment to try rewriting each of these in terms of I. Go ahead and pause the video, and we'll come back and talk about them in just a second. And we're back. Let's look at these two problems together. The first one was the square root of negative 6. I dropped that negative sign and tacked an I onto the outside. So now I have the square root of 6, I. And then I pause for a second and look at that square root of 6 and notice that it's not really a nice square root, so I'm just going to leave it like that in its exact form. For my second problem, the square root of negative 9, I start with the same step. Drop the negative from under the square root and tack on that I to the outside. Then I look back at my square root and ask, is the square root of 9 anything nice? And sure enough, the square root of 9 is the nice number 3, so we'll rewrite this as 3i. The thing to remember about that I is that it's really just a symbol. It allows us to get in and do algebraic manipulations with these non-real numbers. For example, let's go ahead and simplify the square root of 27 times the square root of negative 3. The first thing I'll do is rewrite the square root of negative 3 using an I. That makes it the square root of 3 with an I on the outside. Lose the negative, add an I to the outside. And then it's still being multiplied by the square root of 27. Now, that I can just keep coming along for the ride as I go through the rest of my problem, but I notice now I have the square root of 27 multiplied by the square root of 3. Remember that the product rule lets us push these two things together, making this the square root of 27 times 3. Don't forget that that I is still coming along. Now I have 27 times 3 under a square root. That's the square root of 81 with an I on the outside. And the square root of 81 is a nice number. This is 9i. Whenever you multiply the square roots of negative numbers, you're going to first rewrite any number that needs to be using an I rather than having a negative under the square root. Then simplify just like normal. Let's do another example. I've got the square root of negative 10 multiplied by the square root of negative 2. First step, rewrite these suckers using an I. The square root of negative 10 is the same as the square root of 10 with an I. The square root of negative 2 is the same as the square root of 2 with an I. Now I simplify just like I normally would. The square root of 10 times the square root of 2 is the square root of 20. I times I is I squared. And now comes a little bit of a tricky part. Remember back at the first page where we realized that I squared is really negative 1? That means that we can replace this I squared with the number negative 1. So now I have the square root of 20 times negative 1. Well, that's just negative the square root of 20. And that can be my final answer. Or we could continue simplifying the square root of 20 to be negative 2 times the square root of 5. Either one of those is acceptable. These same steps will work for dividing radicals as well. For example, let's simplify the square root of negative 8 over the square root of 2. First step, rewrite any radicals that have a negative underneath them to have an I instead. So the square root of negative 8 becomes the square root of 8 with an I on the outside. And we're dividing by the square root of 2. Now remember that when you have one root divided by another root, and they're the same kind of root, you can actually do the division before you do the square rooting. So this is the same as the square root of 4 times I. The square root of 4 is a nice number though. That's 2. So this becomes 2 times I. Before I let you try a couple problems yourself, I have one more pointed example for you. We're going to simplify the square root of negative 6 multiplied by the square root of negative 6. So I follow my steps. First step is to rewrite these, each having an I. So this becomes the square root of 6 with an I outside, multiplied by the square root of 6 with an I outside. Now I start simplifying. The square root of 6 times the square root of 6 is the square root of 36. And I times I is I squared. Now, the square root of 36 is just 6. And remember that I squared is negative 1. So now I have 6 times negative 1, which is negative 6. And that's my answer here. I want you to take a moment to notice that it's really important that we didn't try to push these two roots together before dealing with the i's. If I had done that, I would have had the square root of negative 6 times negative 6, which is the square root of 36, which is just 6, rather than negative 6. I would have gotten my wrong number if I had multiplied the 6's before taking out the i's. The product rule doesn't apply to non-real numbers. You do need to deal with those i's first before you do the multiplication. As promised, here's a couple problems for you to try. Go ahead and pause the video and then simplify each of these two expressions that involve some complex numbers. And we're back. In my first example, we had 3 times the square root of negative 2 times the square root of 8. So the first thing to do is to rewrite that square root of negative 2 as the square root of 2 times I. Now I can combine my square root of 2 and the square root of 8, becoming the square root of 16. The 3 and the I are still coming along, being multiplied along here. The square root of 16 is a nice number, 4. So now I have 3 times 4 times I, which is 12i. In my second example, I have the square root of negative 6 over the square root of negative 3. So I start by rewriting each of those to have an I instead of a negative. The square root of 6 times I over the square root of 3 times I. Now I notice that I have an I on the top and an I on the bottom, so I can cancel those out just as though it were a variable. The square root of 6 over the square root of 3 can be pushed together to become the square root of 2, because 6 divided by 3 is 2. The square root of 2 doesn't simplify any further, so we'll just leave it like that in its exact form. The more math classes you've taken, the more kinds of numbers you've learned about. You probably started by learning about whole numbers. numbers like 1, 2, 3, 4, 5, the counting numbers. Then you learned about the negative numbers, things like -1, -2, -3, and we put those all together to be the integers. The integers are the numbers like -1, -2, 0, 1, 2, and so on. Next up, you probably learned about the rational numbers, which are really just fractions, so things that are one integer divided by another integer. Then you learned about the real numbers, which was when we took the rational numbers and added in all of the irrational numbers, so that we had numbers like 1/2 and 2/3 and 7, but also numbers like the square root of 2 or pi. The last addition to your number set is these non-real numbers. When we put the non-real numbers and the real numbers together in one big set, we call them the complex numbers. You'll be glad to know that the complex numbers are probably the last kind of number that you're going to encounter, unless you go on to take a lot of higher level math. In a very deep mathematical way, the complex numbers are complete. There really isn't anything else that needs to be added to them. Now we're able to answer all kinds of questions without ever having to write down, this is not a real number, or we just don't know how to do this. So now we should probably define exactly what we mean by a complex number. A complex number is any number that can be written as a plus bi, where the a and the b are both real numbers. Let's write down some examples of complex numbers then. A complex number could be 2 plus 3i. Those are both integers. We could have -4 plus 2i. The integers could be negative. We could have fractions or decimals. We could do 0.75 plus 2i, or maybe 3/4 minus 7i. Or we could even have irrational numbers. We could have -3 plus the square root of 2i, or pi minus 7i. The big deal is that there's two parts. One part is a real number without an I on it, and the other part is a real number with an I on it. Now, just to show you that the complex numbers really do contain the real numbers, I want you to think about what would happen if the b in a plus bi was 0. If I have a 0 in here for the b part, I'll have a plus 0 times I. But 0 times anything is 0, so that term really goes away, and I'm just left with a, which was a real number. So any plain old real number that you're used to, something like 3, could be written in that complex format as 3 plus 0i, or 3/4 plus 0i, or -7 plus 0i. Any real number that you already know can be written as a complex number by adding on a 0i. The point being that all the numbers that you already know are also complex numbers if you think about them that way. Finally, if the a part of a complex number is 0, that is, it has no real part, then we just call it straight up an imaginary number. So numbers like 0 plus 4i, which we usually write as just 4i, is an imaginary number. 0 minus 7i, imaginary number. -3/4 I, an imaginary number, and so on. Anything that doesn't have a real part is an imaginary number. And all of these numbers together, the ones that have real parts and imaginary parts, or just real parts or just imaginary parts, all of those numbers together are called the complex numbers. Now that you've learned what a complex number is, we're going to look at adding, subtracting, and multiplying complex numbers. Overall, this really isn't too bad. It's an awful lot like adding, subtracting, and multiplying polynomials, something that you already know how to do. You just have to remember that there's one extra rule. I squared is -1. Let's look at a couple of examples. The directions here say perform the indicated operation and simplify as needed. So I look at what I have here. I've got 5 plus 2i minus 3 minus 4i. So I'm doing some subtraction. This 5 plus 2i, I'll just rewrite like that, and that minus, I'm going to remember, needs to be distributed to both pieces of my second term. So -3 plus 4i. Now I combine like terms, just as though the i's were a variable like an x or a y. I've got a 5 minus 3, which is 2, and then I have 2 i's plus another 4 i's for a total of 6i. My second example has 5 plus 2i being multiplied by 3 minus 4i, so this is a multiplication problem. Now, if this was an x here instead of an I, you'd look at that and know right away that what you want to do is FOIL this. So we're going to do the same thing. My first terms multiplied together become 15. My outside terms are negative 20i. My inside terms multiply to be 6i, and my last terms multiply to be negative 8i squared. Now I just need to simplify. I have a 15, I have a negative 20i plus 6i, which is negative 14i altogether. I have a negative 8i squared. Now remember that I squared is really a negative 1, so I can simplify this even a little bit further. Now I've got 15 minus 14i, negative 8 times 1 is plus 8. So finally I'm down to 15 minus 14i plus 8. That 15 and the 8 can be put together to be 13 minus 14i. And of course I meant 15 plus 8 would be 23 minus 14i. Now here's some for you to try. You're going to perform the indicated operation and then simplify as much as you can. Go ahead and pause the video and give these a try. My first problem is 3i plus 2 minus I. Now because this is addition, I can pretty much drop the parentheses, making this 3i plus 2 minus I. Now I just start combining like terms, like I would if I were adding two polynomials. I have a 3i and a minus I, which come together to be 2i, and the 2 doesn't have a like term to combine with, so it comes down as 2. Now my answer now says 2i plus 2, which really is probably just fine, but it's traditional to write the answer as 2 plus 2i, with the I part coming second. So if you check the answer in the back of the book and it says 2 plus 2i, but you had 2i plus 2, don't worry, you just forgot to write the I part second. My second problem was 2 minus I times 3 plus 2i. Since I'm multiplying, I'm going to be foiling these two things out. So I get my first terms, oh, looks like Maddie's trying to help again. So when I multiply my first two terms together, I get a 6. My outside terms give me 4i, my inside terms negative 3i, and my last terms negative 2i squared. So now I start combining like terms. 4i minus 3i is a single I left over. And I'm also going to remember that I squared is the same as negative 1. So now I have 6 plus I minus 2 times negative 1. Now negative 2 times negative 1 is positive 2. Then I can add the 6 and the 2 together to get 8 plus I. Now I have a tendency to write down this step where I go from I squared to negative 1 and then finally to swapping the sign. However, if you feel comfortable, you can go straight from negative 2I squared to plus 2 if you want to. This last problem was another addition problem, 5 plus 2i plus 3 minus 4i. So I'm really just combining like terms. 5 plus 3 is 8, and 2i minus 4i is minus 2i. Before I let you go, I want to show you a couple more examples of multiplying complex numbers. We're going to perform the indicated operation and then simplify. Here I have 2 minus 3i squared. Remember, when you see a binomial type thing being squared, you want to rewrite that so that it's being multiplied by itself and then FOIL. Remember, actually multiplying the thing by itself by FOILing will give you a really different answer than trying to distribute the exponent. So here I have 2 times 2 to be 4, 2 times negative 3i to be negative 6i, and then another negative 6i, and then a plus 9i squared. Now I start simplifying and combining like terms. I have a 4, a negative 12i, and then this 9 times I squared will actually end up becoming 9 times negative 1. So now I've got 4, negative 12i, and minus 9. 4 and negative 9 add together to be negative 5, so negative 5 minus 12i. This last problem is just to remind you that you can use distribution with these complex numbers as well. I have 2i being multiplied by 5 minus 3i. So I'll distribute the 2i to each of the two terms in here, giving me 10i minus 6i squared. Now I'm not quite done yet because I squared is the same as negative 1. So this is 10i minus 6 times negative 1. But negative 6 times negative 1 is positive 6. So this is 10i plus 6. And I'll finish up by writing my answer as 6 plus 10i, with the imaginary part coming second. And of course, I have a couple problems for you to try. You're going to perform the indicated operation and simplify. I want you to be really careful to pay attention to which operation you're performing. Are you multiplying or adding or subtracting? It makes a big difference to your final answer. So go ahead and pause the video and try these two problems. And we're back. On this first problem, I had 3 plus 2i and 4 minus i, and they're being multiplied, which means that I'm going to FOIL. So I multiply my firsts, my outsides, my insides, and my lasts to get 12 minus 3i plus 8i minus 2i squared. Combine my two I terms to get 5i, and then remember that I squared is really negative 1. So that gives me 12 plus 5i, and then negative 2 times negative 1. Negative 2 times negative 1 is just 2, and 12 plus 2 is 14. So I end up with 14 plus 5i. For my second example, I have the same two numbers, 3 plus 2i and 4 minus i, but they're being added this time. So because they're being added, I can essentially drop the parentheses and just combine like terms. 3 and 4 is 7, 2i, take away 1i, is a single i left over. And just in case you felt like you didn't get enough practice, here's 3 more problems for you to try performing the indicated operation on and then simplifying as much as possible. Go ahead and pause the video and then we'll go over them together. And we're back. My first problem was negative 3i multiplied by 4 plus 5i. So I distributed that minus 3i to each of these two terms, giving me negative 12i and negative 15i squared. But that I squared is eventually going to flip the sign on the 15, making this 12i plus 15. And then I can rearrange those to be 15 minus 12i. My second example is an example of subtraction. Here I have negative 3i minus 4 plus 5i. So I'm going to distribute that negative to each of my two terms, giving me negative 3i minus 4 minus 5i. Then combine like terms to get negative 4 and negative 8i. My last example is 1 plus 2i squared. Now right away I know that I need to write this as 1 plus 2i times 1 plus 2i so that I can remember to FOIL. When I FOIL this out, I get 1 plus 2i plus 2i plus 4i squared. The two 2i's combine to be 4i's. So now I have 1 plus 4i, and then I'm going to remember that this I squared is really negative 1. So I have 1 plus 4i plus 4 times negative 1. Now 4 times negative 1 is negative 4, so now I have 1 plus 4i minus 4, and the 1 and the minus 4 combine to be negative 3 plus 4i. That wraps us up for section 7.7. I hope you enjoyed this introduction to complex numbers and that your homework goes well.